So in this part, we will talk about the residual method, or what we call it also the strapping method, or it's the same, or the feathering method. And we will see why we call it those kind of terms or names. Okay, I will just review a little bit what I did, and this CB at certain time equal okay. This is our model equation, and then what I did, I will have it a large profile, so make it easier to. I will use log CB, so I transform it already rectilinear, so I'm using this one, this, okay, and then versus time, and let's go with profile, which will be curved, right, and then linear. Okay, to determine K, as I just mentioned, we took 3 or more points at the terminal phase. We do a linear regression of it, and I can determine from this slope minus K over 2.303 because it's log, and I can determine the half-life of elimination. Okay, this is what I just said in a minute. I can do a extrapolation, okay, of what? Of the terminal phase linear regression, which I can use to determine what? The intercept, right, which will be equal to log the whole constant. Then I need to, this is what we did already in this part, so just whatever you know. Now I will use this method to determine, we determined K, we determined the half-life of elimination. Now I want to determine what? Ka and its half-life of absorption. How we will do that? This will be called the profile, which is, wait a second, this profile, okay, which is in fuchsia concentration. I will have time, I will have log CB, right, at certain time, which is what we already have it in fuchsia. This we will call it observed concentration or measured concentration, right? Because it's what we already measured. So this is will be observed. Okay? What we have it here, the one I have it here, which I will again, I love colors. That's why it's easier. It will be easier for you to follow me. So it will be this one, log CB extra, which will be extrapolated. Okay, again, this is the green one. Okay, this is called extrapolated line. Okay, this is called observed or measured concentration. Okay, this is the terminal phase, which is related to elimination, right? I will take not this color, this is not right. I will take 3 or more concentration on this. I will have different different measurements, right? This will be what I already have here, right? And this one, I will have 1, 2 numbers, right? 3 and 4 at T1, T2, T3, and T4, right? Log extrapolated, I will take 3, 2 more, so it will be 1, 2, 3, and 4, okay, at the extrapolated line. How I can do that? You just substitute different time in the equation that you have it here from the linear regression, right? Ax plus b. This is minus, this is the slope, this is your log, the constant. So if you have different times here, time that we have before the Cmax, at different time point, take different time points and then substitute it in this equation, you will have it as extrapolated. بالعربي المعادلة اللي طلعت معك هون شو بتعمل فيها؟ بتروح بتعوض different time points قبل السي ماكس، بيطلع معك الايكويشنز اللي هون، صح؟ لأنها هاي امتداد extrapolated of whatever that we have here. Done. فأنا I will have now the extrapolated line, which is extrapolated equations. I have the observed, okay, both of them. I will do one thing, which is the difference or the residual, okay, which will be, because we have it log, of course you may have it as len, or you may have it on semilog, and we will have an example on that. This will be the log CB difference, which will be equal to log CB extrapolated minus log CB what? Observed. So it's that I'm taking whatever in here at each time point minus this, this minus this, and this minus this, and this minus this, okay, at each time point, which is minus this, this minus this, and so on and so forth, to have 1, 2, 3, and 4 or more what? CB differences or CB residual. And then after that, we will draw it, okay? I'm drawing this log CB difference in blue, okay? If we are on log CB, it will be linear. I can do a linear regression. This is at the beginning called residual line or feathered line, residual line, because we are taking the difference between two kind of things, and this is in this statistic called residual. Stripping line, because you are stripping your profile into different line. One is that is related to elimination and the other related to absorption. And feathering, because it seems like feathers, the profile is separated to feathers. And because we have one compartment with only two processes, you'll have one related to the elimination and one related to absorption, okay? That's why we call it the residual line. And now this what we have in blue, okay? We can do a linear regression for this residual line. I will have another equation, okay? I will change the symbols to make it easier to not confuse yourself. So this will be the slope that will be equal to minus Ka over 2.303 because we are talking about log. Okay, and this will be the same. That's why I will return it to b, okay, which will be log the whole term. Okay, so we have here the same intercept because we are starting at 0, and we will talk about the lag time in a minute. Okay, if we are having the, you can determine Ka, and if you can determine Ka, okay, you can do what? Determine the half-life of absorption, which will be equal to 0.693 over Ka. So we use the residual to determine Ka and to determine its related half-life, and it's not working anymore, to determine Ka and its half-life. This is the residual method, and one paper with a lot of colors. So I hope that you enjoyed it. It's something important and it's something easy to know, but you need just to follow the steps. First, let's color it in one different kind of things. Type. I have a lot of pink and fuchsia colors, which is make it hard. Okay, so we will do the terminal phase linear regression. We will have the extrapolated line, okay, and then we will subtract both of them, both the extrapolated from the observed to have the residual. Okay, so it's 3 different steps. You have the extrapolated already from the terminal. You have it in the previous paper or the previous explanation. This is the second step, and this is the third step, which you already got it from whatever I know I told you. Okay, so again, let me just have some line here. Okay, to not confuse ourselves. And this is, so this is our table. Okay, and that's it. So this is the method to determine the Ka and its half-life, which is the residual, because we have the residual line. The terminal was used to determine Ka and its K and its half-life. So the terminal linear regression, the terminal phase linear regression to determine Ka and half-life, as we said, in a minute or a couple of minutes. Okay, but I need to do this to determine the extrapolated line, okay, which is needed to determine the residual line. So the terminal linear regression is needed to have this part, which is the extrapolated line, and then I needed to determine the residual line. Again, I have it in log term, but you again can have it and whatever the profile that I have, right? So you can have it as, are we in? Yes. You can have it as semilog, CB versus time, and you can have it as CB versus time, len term, rectilinear. On the semilog, you will have it like this, extrapolated line, and like this, linear again, and len, and like this. The difference is this will be your constant as it is, and here will be len, your constant. In here, we need to either use the do the processing of the data that we have, or exponential. And here, this will be minus K, and you can determine half-life of elimination. And in here, you will have minus Ka, and you can determine the half-life of absorption from it. Again, this is under the assumption that the elimination is my rate limiting step. So again, we are talking in all what I mentioned earlier, that the absorption is faster than the elimination. So my elimination is rate limiting step. Okay. Another thing that's why we have the terminal phase that is related to elimination. Okay, terminal phase related to elimination and terminal phase related to elimination because of this. Okay, and all of that is explained step by step in your slides with the profiles and with details of the profile. You have in your slide 28, okay, this profile CB difference, which is the same as CB residual versus time on a similar graph, and we have this, just this profile. This is the same as CB residual, okay, which is this is the same as this profile, but we are having it on a separate profile, which means you can have this on a separate profile. It's called CB residual or difference, and this then CB residual or difference by itself, or this alone, but it's just visually easier to have it. Okay, that's it. In all the residual line, we are drawing something that is related to absorption, right? Which is, this is the one related to absorption. If we go back to our equation, at the beginning, we said when we did the terminal phase linear regression, we were assuming that we reach enough time point to what? To have complete absorption, and it's equal to 0. Now, this exponent term, it's equal to 0. The residual line, we are having the elimination, and we remove from it what is observed. We subtract whatever is here from here, right? Which means it's similar to that I don't have elimination anymore. So that's what you have in your 29th slide, which is that this profile, which is an H profile that we have, whatever the graph that we are drawing, it's having CB difference, which is the same as residual, equals the constant, the whole constant multiplied to just Ka with time, which is related to absorption. Okay, and by this we ended the residual method, but we need to say a couple of notes about it. First of all, to do any linear regression for the terminal phase, or to take whatever that you have here, or on the observed line or observed profile, and the residual to do a linear regression, we need at least a 3-point. So to take the straight line here, straight line here, straight line here, to make it accurate, you need at least 3 points or more. Why? Because it's common sense, and I'm pretty sure you know it, because if you take just 2 and you don't have the third one, right, which could be here, which could be here, and could be here, this will be your 9, this will be your linear regression, or this, you never know. So you need at least 3 points or more to have the linear regression or the straight line. Okay, the time data points occurring directly after the Tmax or Cmax, usually it's not accurate to represent the elimination phase, because sometimes you have post-absorption here, which is the post-absorption phase, and I need to make sure that I'm reaching the period or the time where I have the terminal phase only, in which we have only the elimination and no absorption in it, because we have absorption here according to whatever I said before. To use the residual, you need to have a linear kinetic for sure. Okay, that's why you'll have linear lines, and to make it accurate, we need to have a difference between the steepness of this profile with the steepness of this profile or line. The steepness of this line with this line, which is one related to the elimination, one related to absorption, which means to be accurate, not that you can't use it. I will ask you a question in the exam, inshallah, if we have exams, that what is Ka and what is K, for example, okay? So to use the residual, we need to have, as rule of thumb, at least 5-fold difference between both of them, as rule of thumb, which make it more accurate, because the steepness between the first profile and the second profile should be enough so we can determine both of them, okay? To make it more accurate, we should have this kind of difference, but it's not, let's say, rule. So you can determine it even if it's less, but it's more accurate to have it with 5-fold differences, okay? And by this, we end the residual method.